So what I want to do is continue on with some examples in the relevant context that we've been talking about. So in my last example was sort of a little bit about what happens when people put in solar PV. So this one is sort of related to that and talking about feed-in tariffs for people that put their surplus energy that they produce from their panels into the grid. So what I've got here is some details on what kind of rates that you get in different states for putting in your energy at different and the regime varies across the states. You can see though that there's in most jurisdictions there's some sort of similarity, that this is sort of around the marginal cost of production in most jurisdictions. That is the way that they're providing incentives. There was some period in the past where the feed-in tariffs were much higher. So let's have a look at my sample again, and we've got two setups now. So we've got the feed-in tariff when we've got a high feed-in tariff and a low feed-in tariff. So we've had this scenario where feed-in tariffs have changed. So at some points they're high and some points they're low. So we've got these multiple measurements on people. So we've got a little bit more information. Same basic data set. We're looking at energy consumption. And we've now got feed-in tariff. So the FIT is the feed-in tariff variable, and it's describing things when we have regime 1, which is high, and regime 2, which is low. So if we're talking about Western Australia now, we would be in regime low. Okay, so there's been a change in the feed-in tariffs. So let's have a look at this. So we want to make this sort of a stylistic question. So we're going to flip it around a little bit and say, what happens to electricity consumption after an increase in the feed-in tariff? So the idea behind this would be that, well, we have measurements on households, and we would have measurements before the increase in the feed-in tariff and after the increase in the feed-in tariffs. So we'd be able to conduct a paired t-test. And in this setup, we're going to look at just the Victorian data. So because we're just looking at the one jurisdiction, we have a paired t-test for the matching data in Victoria. First step, we create a box plot. All right, it's a paired test, so we like to go for this horizontal setup, and you can see again that the that zero, where that 0 point is. So if you just eyeball the plot, it looks to me like mass of the observations is looking pretty close to 0. So from this plot, I would be thinking that, my null hypothesis is 0, I'm not going to be rejecting the null hypothesis. So let's have a look at our formulation. So we're just going to say the mean of the different series is 0. Okay, so you can frame that. So what does it mean? It means that energy use before the change in the feed-in tariff and after the change in the feed-in tariff are the same. That's what it really means in practice. We can have some general language to cover all cases, and that makes life a bit easier for us at this stage. But in the long run, you'll start shaping your null and alternate using the actual context that you're working with. But to get started, it's okay to use these general statements. We're also going to have our alpha at 0.05, which is going to feed into our decision point, and we want to implement the test. So how will we implement the test? If I can just show you through that. So we've got the with command, energy1, so that's the name of my data object in R. So remember, I would have read in the data from my Excel file, which would have been in CSV format, and I'd have energy1 is my name. I want to apply the t-test. I've got Vic PV feed-in tariff low, Vic PV feed-in tariff high. So they're the two columns of data. Paired is equal to true. And then we're just looking at this guy at the p-value. So the p-value is above 0.05, therefore we would not reject the null. All right, and you can see, we might think, what does that mean in practice? In practice, it means that we've no evidence, or we have insufficient evidence that there has been a behaviour change once the feed-in tariff came into effect, or the change in the feed-in tariff came into effect. Now, one thing that I would point out is a paired t-test is exactly the same as a single sample t-test on the different series. And we can see that if we look at the way that we can implement this test. So here I have the paired t-test. So you can see there, paired t-test equals true. And these are my two values. If you look down here, I've entered them in directly. All right, so this is going to give me a single sample t-test, and you can see here, one sample t-test, but it's got variable 1 minus variable 2. So I've created the different series. So it says apply the single sample test to this object, which is each paired observation subtracted. So it's a single sample t-test directly on the different series, and you can see if you look at the p-values, exactly the same. So that's the idea. When you have a paired t-test, it's exactly the same as a single sample t-test on the different series. But you don't have to create the different series. We find it easier to specify this as paired equals true. So we can continue on with some more examples. And again, I'm working on pollution and some of the negative effects of energy production. So we're looking at sulfur dioxide levels. So this is the example here, and we might be looking at what's going on in sulfur dioxide levels over this period in China. You can see there's a lot of red on this plot. So a lot of red is going, this is very high SO2 levels. So why might we be concerned about SO2 levels? Well, we might have some impacts from acid rain. So this has been a problem that's experienced in some jurisdictions. We've been fortunate in Australia to not really have had a huge amount of problems with this. And, acid rain can be really taking its toll on our infrastructure. It's really wearing things away. We can see things that are happening in terms of smog. So when we have pollutant matter in the air, it has this negative effect on visibility. We can see that, we can have really bad days and things can be materially affected. This is really something that's happened. And there's also impacts on human health. And, these examples that we're looking at are China. So it's a place that's developing, lots of change, lots of policy changes going on as well. And you can see that this is quite a big documentary on this topic. So it's, the problem of air pollution in China. So these are real problems that we face. So what's the context of our test? And we're going to have a few related to these. So the first thing we're going to think about is, well, are there regional differences in sulfur dioxide levels in China? And we know that energy generation is going to be a major driver of this. So industrialization that relies on that energy is going to be, playing a part in this. So we've got two different samples. So we're going to compare the north and the south. And we want to know is, well, are the pollution levels, or in terms of SO2, different in the north and the south? So two different samples. First step, what do? We're going to have a visual plot. And personally, I find the visual quite compelling. It seems to me that pollution levels in the south are actually less than in the north. All right, you wouldn't say that there's no overlap in the data sets, but I do feel, looking at that when I look at the mass of the box in the middle, there's not really any overlap in the box, and that's really for me a sign that probably there are some differences here, and that the sulfur dioxide levels in the south are actually lower. But we want to have a formal test, so we want to implement a formal t-test. Before we can implement the formal t-test, because we have two samples, we have to have the variance ratio test. So we set up our variance ratio test, which is just variance in the north is the same as the variance in the south. Our alternative is variance in the north is not the same as in the south. Alpha is always 0.05, and we want to conduct the test. And we're going to apply the p-value decision rule. So if the p-value is less than 0.05, we're going to reject the null of equal sample variances. So let's have a look at our test. We're getting a real hang of this. So with the data set SO2, it's in wide format. That's just the name of the data. Apply the variance ratio test, and the two columns in my data frame are north and south. So we've compared them, and we've got a p-value of 0.01. So if we get a p-value of 0.01, we're going to reject the null of equal group variances. So when we implement the t-test, we're going to use the formula that says the variances are different. So formalize the test. The null is, so this is the test for our t-test. The null is that the mean pollution level in the north is the same as the mean pollution level in the south. So we're talking about the means. We're really, are these two samples drawn from the same population? Our alternative is just insert the word not. So you can really follow that structural pattern, set up the null, set up the alternate, and you can just continually follow that pattern and you'll be okay. We know that we need to apply this with the unequal variance formula. So let's go ahead and do that. With our data frame, apply the t-test to the two variables, north and south, variance equals false, because we've already decided from our test that the group variances are unequal. And we get a p-value that's a very, very small number, so we know based on that we are going to reject the null. We're going to conclude that the pollution levels in the two jurisdictions are different. So, and what we're going to know is that we know in here, so look at this, X is the north, the south is the second one. So it follows the same pattern that you specify up here. So we know that actually the pollution levels in the south are lower. How do we know? So the test just told us that they were different, but if we look at the full test output, we can see that they're in Y, are they lower? And if we look at the 95% confidence interval, we can get a sense of how different they are. So it says, look, the true difference between them is probably somewhere around 160 to 178 units. So that's it's actually quite a big difference between the north and the south. So we can see up here, we get a decision rule about yes, no, what is the, how do we make a decision on our hypotheses. Down here, from looking at the means, we can work out which mean is bigger and which one is smaller. So in this case, smaller is better. We want less pollution. And if we want to know about, about what's a good representative range for the difference between the two, this bracket here, the 95% confidence interval, tells us what we think is, this is, probably a good range to think of how large the difference between these two samples are. And that's an opportune time for a break.